Okay, so we're recording. So this is a picture proof of why Pythagorean theorem has to be true. And so we can use it with these toys. So again, we pick up these triangles, we plop them down in the right spots. And take a snapshot of this. And what have we generated when we put those triangles in there?
Another square.
Another square, yeah, we have made another square. And so let's put that in the notes. Just want this square right here. And they do really fit in there nice. Again, if you look at this, the original version of the triangle, those four corners, the ones on the corners are just copies of this one right here. And this triangle right here has a length that's common with that square. It has a length that's common with this square, and it has this long length that's common with the big square. Okay, so they're designed to have congruent sides. It was built that way. And so we can build this new square over here by putting the triangles together with the other one. All right. So question, what are the dimensions of this new square? If this little edge right here is length A, this medium edge is length B, and this longer edge is length C. What is the distance across this figure?
A plus B.
Yeah, it's A plus B. And what is the height of this figure? It's A plus B again, isn't it? Yeah, yeah. So I can take those extra copies of the triangles and I can make a new square that's has a total area of A plus B times A plus B. So the new area there is A plus B times A plus B. All right, so we're going to do that again. We're going to pick the triangles up and we're going to reposition them. So this time what we're going to do is we're going to take the triangles, and what you should find is they should fit nicely along each edge of square C. And this makes this other new, beautiful, but different square. And what can you tell me about the length of this square? It's A plus B. And what about the height of it? It's A plus B. It's the same size as that other square. They are the same size. It's kind of neat. Stick it right there. Okay. So what do they have in common besides they have the same base and height? What's that? Well, because they have the same base and height, they're congruent. But what else do they have in common? I mean, they're different, aren't they? In a way, how are they different?
What is it, like the insides? Yeah,
the insides are a little different, right? This one here has these two yellow squares. This one here is the red square inside, because that's how they're different. How else are they alike? They both have the four triangles, yeah. They both have the four triangles. So if I take away the four triangles from both figures, don't the remaining areas have to be the same? If they started off to be the same? So if we do that, if we pull off this triangle and that triangle and that triangle and that one here, and we pull off those four triangles here, what that tells me is that the two yellow squares have to have the same area as the big red square. It's got to be that way. Now, there's nothing special about the triangle I drew. You can repeat this process with any size triangle. You just make the triangle, you make the three squares of the same, with the appropriate lengths, and you make some copies of the triangle, and you can always make this happen. Happens every single time.
Does it have to be a right triangle?
Yes, that's the catch. It's got to be a right triangle. Yeah, the Pythagorean theorem only works for a right triangle. And in a couple of activities, we'll explore that idea, when it works and when it doesn't. Right triangles versus non-right triangles. Okay. So this is a picture proof of the Pythagorean theorem. Okay. Pretty cute, huh? I just thought it was pretty cute. It turns out there was an American president who proved the Pythagorean theorem in a way that had never been proved before, which is pretty remarkable. I think there's like maybe 100 different proofs of the Pythagorean theorem, 100 different ways to show it's got to be true. And in the, was it late 1800s, this guy came up with a way to do it no one had ever seen before. And it's really interesting. I'm not going to tell you which president. But I can show you the proof, and you guys can see if you can find out which president it is. And then I'll give some points for whoever can tell me who that president was. So let's take a look at the proof. To do it, we're going to have to do a little bit of algebra. So that was a proof kind of without algebra. Here's a proof with algebra. So what we do is we take, and you can kind of trace this out on your paper. Just grab one of those triangles that you had. So let me grab one here. Where'd they go? Which one? So put you right there. Does that one work? No, I want this other one. So most, by the way, the software I'm doing this in is in Google Drawing. And most drawing tools these days allow you to make all kinds of shapes. And one cool thing about them now is they kind of show you how shapes line up with each other. And so it's guiding me to help kind of drop it in the right spot. So it's a pretty nice tool for playing around with geometry stuff. Where sometimes, you know, compared to GeoGebra, it just does different stuff. All right, so let's see. I need a screenshot of that. Screenshot. Wow, I did it wrong. Oh, I got to draw a rectangle around it. Oh, I don't know if this is going to work. All right, I'm going to try it different. Let's see. Will this thing let me draw triangles? Ooh, it lets me draw right triangles. Okay, I think I can make it happen here. So there's a similar triangle to the one you guys have there. All right, can I make a copy of it? And so you're going to need two triangles to do this proof. Control C, Control V. So one is going to be rotated 90 degrees compared to the other. And then I'm going to pick that one up and I'm going to stick it right so that toes meet up there, the little points, and not right there. I guess that's probably as close as it's going to get. Close enough. All right. So when we put these two together like that, so the next thing we're going to do is we're going to draw a line connecting these upper vertices. So you could trace this out on a piece of paper. Let's see, where's my line tool? Let's use a different color. Black. Okay. Cool. Got it. So what do we have here? We have a new shape. What is it? Think of the outline of it.
Is there isosceles?
It's not isosceles. How many sides does it have? You got 4 sides. Yeah. So I put so the bottom sides are in the same plane, in the same line. So that's all one side there now, and they're supposed to be connected. So make believe they're connected there.
It's a trapezoid.
It's a trapezoid, yeah, because I have a pair of parallel sides here. So this is a trapezoid. All right. So this is a trapezoid. Trapezoid. And this trapezoid is based on 2 right triangles, 2 copies of the same right triangle. Based on 2 copies of same right triangle. All right, so let's label some things here. According to the picture I had earlier, this little length over here, I was calling that A. The bigger length I was calling B, and the long length I was calling C. So that's C over there too. This is A down there, and this is B. So as far as the area of a trapezoid, the area, the formula is take the 2 bases, that would be this one over here, A, and this one over here, B, and average them. Okay, so I would take A plus B over 2. And I would multiply that by the height, and the height would have to be this part right here, right? And that's just another A plus B. So that's one way to view the area. There's another way to view the area. Haven't I dissected this figure by the way I built it? Okay. It's the product of, it's the composition of 3 triangles. So this blue triangle right there, what's the area of this blue triangle, knowing that that's a right angle? But I'll jump at once.
1/2 A times B.
Yeah, 1/2 base times height. So 1/2 A times B. So 1/2 A times B. And I get another one of those, right? So I have two of those, 1/2 A times B. Question, what kind of triangle is C here? You said something about it earlier.
Isosceles.
Yeah, it is an isosceles triangle, but I think it's more than that.
Is it a right triangle too?
Yeah.
Why is it a right triangle? Oh, you guys are good. Yeah, why is it a right triangle?
Magic.
Magic. Okay, there's another reason besides magic, so check this out. Wrong pen. Across the bottom, would you agree I have a straight angle across the bottom if I focus on that point right there? Okay, so that straight angle is made up of three angles. This one right there, this one right there, and then this bigger one in the middle. So I'll label them with little arcs. We have angle 1 arc, angle 2 arcs, and angle 3 arcs there. So this angle right here happens to be the same as that angle right there. And this angle right there happens to be the same as that angle right there. What do we know about this single arc angle and this double arc angle? I'm going to call them angle 1 and angle 2.
They're equal to 90.
They have to add up to 90 degrees, right? Because they're in a right triangle. And so they have to be, the other two angles in a right triangle are always, is it complementary or supplementary?
Complement.
Complementary, correct, yeah. Angle 1 and angle 2 are complementary. Since angle 1 and angle 2 are complementary, their measures add up to 90 degrees. Since I have a straight angle through here, straight angle has what total measure? 180. So what's that leave for that middle angle? Angle number 3? Yeah, angle number 3 has got to be a right angle. It's got to be a right angle. So it turns out that's a right triangle too. So the cool thing about that is its area is 1/2 C times C. Because angle 1 and 2 are complementary. And that's a straight angle at the bottom. Does that make sense? Piecing that together? Okay. So now what we're going to do is we're going to put these two formulas together. So we're going to take this one version of the area as a trapezoid, and we're going to compare it to the same area as three triangles and see how it shakes out. So rewriting that, we've got a little algebra to do now. We usually don't do algebra, but we're going to branch out a little today. So I've got a plus b over 2 times another a plus b. And I could put that in parentheses too, like that. And it has to be equal to our 1/2 AB plus our other 1/2 AB plus our 1/2 C times C. Is it okay if I call that C squared? So this divide by 2 out front here, I can just pull that out as a 1/2 instead, because multiplying by 1/2 is the same as dividing by 2, isn't it? So then what that means is that leaves me on this left side to multiply this guy by that guy. So do your best to multiply a plus b times a plus b, see what it shakes out to be. I'm going to rewrite my board quick because it was slipping. What is a plus b times a plus b? Oops. Thing. So that's what I get at first shot. I have to distribute first the a over here to the other two terms, and then the b to the other two terms. So I get a squared plus ab plus b squared. But the ab's are like each other, so I could say I have what instead of a plus a times b plus a times b. It's really 2 ab's, yeah. So the 1/2 is still chilling out front. So we have a squared plus 2 of those ABs plus B squared. So we can clean this up a little bit more. I could multiply that 1/2 through there, or I could leave it hanging out. Any decisions there? What do you want to do? Move it in, leave it out, move it in. So then I'll have a 1/2 A squared. 1/2 times 2 is just 1 times AB, or just AB. And then I'll have a 1/2 B squared. All right, I've been ignoring the other side. Can I clean up the other side at all? Aren't those first two terms like? So if I have half of something plus another half of the same thing altogether, I must have one of them or a whole. Yeah, so on this other side, I'm going to come all the way down here. I have a whole AB there. And I have half of that C squared. Okay, now that I've cleaned up each side, I can start comparing the sides to each other. What do you notice about the left and the right sides? They have the matching AB. So if I were to say, subtract the AB from one side, I would have to also subtract it from the other side, in which case it's gone from the equation. I can pull it out and I'm still balanced. So that leaves me with 1/2 A squared plus 1/2 B squared equals 1/2 C squared. What else could I do? Tidy this up just a touch more.
When all the halves cancel.
If I multiply both sides by 2, yeah, that's exactly right. So I could consider multiplying both sides by 2. Distributes through there, multiply this side by 2, and then I get what the world has known for thousands of years. Shrink this a little bit. Ooh, so I'll squeeze it in underneath anyway. That A squared plus B squared equals C squared. Most elegant depiction of it. My pen is struggling. Right. Yeah, so that a president in the past, not in the last century, can't discover this version of how to show the Pythagorean theorem is true in a way using this trapezoid nobody else had ever seen before. It's pretty awesome. I know presidents have made a lot of remarkable accomplishments of the world. Usually it's in terms of like peace or whatever other things presidents do, but there's not many presidents that have contributed to the world of mathematics in such a beautiful way. Because of this, he's my favorite president ever, even though he wasn't around during my lifetime. So yeah, there's a ton of different proofs of the Pythagorean theorem. Some of them are picture proofs, like the one we did first. Others are kind of geometric algebraic. There's just so many different ones out there. Will you guys prove the Pythagorean theorem with your students? Not really. You could kind of walk them through the cutting out and comparing the triangles we did first. That's pretty doable for certain older groups. But, more it's for you, not for them. To kind of get an understanding. It's a remarkable thing, true. All right, next, let's take a look at, we have a couple of activities to look at. And on the course website, I posted that we're going to do activity 5 and activity 7. I guess these are out of order. That sucker there. So activity 5, you need this puzzles worksheet, and you need to cut those pieces out. So if you haven't cut those pieces out already, please cut them out. And then you should have the packet that says what we're going to do with these. So for those of you watching the video, this next part's going to be pretty lame for a little bit. We're doing activity 5. Cut those suckers out, start taking a look at the directions, and we'll see what we got.
This one?
Yes, that's correct. And then the graph paper is for the next one.
You cut out all of them?
You cut out all of them. Yeah. And the activity sheet, you want to get that out to look at too, tells you, kind of guides you what to do. So for puzzle 1, it says cut out square A, the 4 pieces of B, to put them together to try and build square C. So it's kind of another picture proof of the Pythagorean theorem. This is a pretty cute one too. What's that?
Isn't cute hard?
That was my old instructor. For me, cute just means fun and awesome. Beautiful. No, I don't believe we need the angles like that.
Is this dark area considered?
That's part of the thing, yeah. That's our right triangle for the Pythagorean theorem here. Oh, it did say measure the 3 angles. I lied. Sorry. I read that before. I forgot all about it. Oh, that's here's my protractor. There.
I think it just.
What's that?
It's just trying to look so it's a right.
Yes, yeah, I think it's pretty clear it's a right triangle. I'm going to try to measure those other angles just for fun. I get about I guess 35 degrees for the little one. Big one ought to be 55. Maybe. Yeah. Yeah, I think they're 35 and 55 roughly. What do you think, Nikki?
That's what I got too.
Yeah. Yeah, so 35 and 55 fortunately add up to 90 with like it's supposed to be, they're supposed to be complementary. But the big deal there is that angle, the big angle is a right angle, it's 90 degrees. And the claim is that we can take those pieces of B and figure A and build the area of square C.
So cut out B.
Yeah, cut out B, yeah. And I think what should happen, I'm trying to sketch it in here, is we should get a picture that looks something like this. When we take the fragments of B and put them up in the corners, A should fit in the middle quite nicely. And so what we can do is we can take C and decompose it as pieces that make up all of A and B. So again, what we get is the square from A plus the square from B are exactly the same area as the square from C by that rearrangement. So it should look something like that once you put it back together. Is anyone having trouble with that rearrangement? No, just write down what our conclusion is. So that's puzzle number 1. If you haven't already, cut out puzzle number 2.
So it says to trace it and cut it out. If you want to trace it and cut it out.
Let's see, where are we? Cut out 5 pieces, put 2 triangles and 2 pentagons together to form a square. Place the square on a sheet of paper, trace around the perimeter, and then cut out that square, label it B. Yeah, so you need to do that, trace it and cut it out.
Is it supposed to be cut out?
Out of a new piece of paper, so let's see, I guess.
I'll put that